Hello everyone. In this lecture, we are going to study rotation in Inviscid world, and in particular, we are going to learn a new technique on solving irrotational flows analytically in Inviscid world, and that is what we call velocity potentials. So we are going to learn that, and then in the next lecture, I'm going to talk about another technique for solving these flows, incompressible flow, 2D flows, which is known as stream functions that we can use to solve some simple flows analytically or some canonical flows analytically. So let's get started with the velocity potential. So first, we want to study rotation in the Inviscid world. So in the Inviscid world, we have Euler's equation as the momentum equation. So dv over dt equals to minus grad p over rho minus g grad h, which is the gravitational force. So this is kind of the momentum equation in Inviscid world, and then we talked about Navier-Stokes equation, which we also had viscosity, but now for simplicity we are going to ignore that and only focus on some flows that have no viscosity to be able to find some analytical solutions for this. Okay, so let's now define velocity potential. What is velocity potential in this context? Okay, so if you have an irrotational flow, meaning based on the definition of a rotational flow, that means that the curl of velocity should be 0 everywhere. So for these kind of flows from math, we know an identity that curl of grad of grad is going to be 0. If you take the curl of a grad, it's going to be 0. Okay. So now we use this identity to define based on this identity, we can define a function phi, which is called velocity potential. So we define this phi as this grad phi is just a velocity vector. So we define a function in which its gradient is going to be velocity, and so this will satisfy the irrotational flow, right? Because the curl of grad is going to be 0, right? So this is a mathematical identity, and this also is valid for irrotational flows if grad phi is velocity. And so then we call this phi as a velocity potential. Okay, so let's see what are the different. So if the velocity components of this, so if the velocity vector is u, v, and w, So we can define this u as partial phi or partial x, and v as partial phi or partial y, and w as partial phi or partial z. Okay. So this is the different components of this gradient vector that we defined. This is how it's going to be defined. So this is actually showing the velocity potential, and it is going to be actually perpendicular to the streamlines and the velocity vector. So say if we have these velocity potentials here, and then these phi 4, this is phi 4, phi 3, phi 2, phi 1. So this is greater, phi 4 is greater than phi 3, and this is greater than phi 2, and phi 1 is the smallest one here for constant phi here. Then how the velocity is going to go, so it's going to be going from low potentials to higher potentials, right? So here, for example, partial phi over partial x, because this is positive, because partial phi, if this is x, so partial phi over partial x, so let's say this is x and this is y, this is going to be positive. So we need to have a u, a velocity vector in this direction, and also, so it's going to be something like this here. It's going to be a velocity vector, and in this direction, it's going to be like this, right? And this is going to be always perpendicular. The velocity vector is going to be perpendicular to these velocity potentials, okay? So what happens is that velocity goes from low potential to high potential. This is how we define this, right? The velocity potential. So when the potential is higher, the velocity goes from those low potentials to high potentials. It might be a little bit counterintuitive compared to pressure gradients, because we have, when pressure is higher, the pressure goes from high to low, so it's a little bit different. But here we have the velocity potentials, where it means that the flow will go from low potential to high potential. So it's kind of against the pressure gradients. So this is how actually we are defining. This is kind of a definition of velocity that we made for these velocity potentials. Okay, so now we want to investigate this further. So if the flow, in addition, if the flow is incompressible as well, we can write that the divergence of velocity is going to be 0. And for velocity, we just define it as grad phi. So this means that the divergence of grad phi is going to be 0. And this means that the Laplacian, or grad square of phi, is 0. This is an interesting equation for the velocity potential, and that's why we are using this, because this is Laplace's equation, and more importantly, this is linear. So now we are dealing with a linear system that we can solve it analytically. So previously, this kind of system is nonlinear. We have a lot of nonlinearities. But if the flow is irrotational and incompressible, we can define a velocity potential in which it satisfies the Laplace equation, which is kind of a linear equation. Okay? So for irrotational, incompressible, inviscid flows, the vector velocity field can be described by the gradient of a velocity potential phi, and the Navier-Stokes equation is replaced by the linear Laplace's equation. Okay, so this helps us to be able to find some analytical solutions, because now we have a linear system and we can actually solve this analytically, this system. Okay, so now let's solve two examples. One example I'm going to solve this session, and the other example I'm going to solve in the next session. Okay, so example: find the velocity potential for a uniform flow. So for a uniform flow, let's find the velocity potential. So say here we have, let me do it with this. Okay. So by a uniform flow, we mean if this is x direction and this is y direction, the velocity vector is going to be ui, is just a constant, right? So here, for example, it's going to be u, and it's going to be u everywhere. It's a uniform flow. Okay. So let's find this velocity potential for this. So u, based on this definition for the velocity potential, is going to be partial phi over partial x. Partial x. So phi, the velocity potential, is going to be ux plus c, right? So this is going to be our velocity potential. And we can set this C to zero. Okay. And so then our velocity potentials are going to be like this. So the first one, if I want to plot them, is going to be here. Is like phi 0. Then the next one is going to be here. So say phi 1 equals to u. So it's just linearly increasing, right? Linearly increasing. So let's see. And then the next one is going to be here. Phi 2 is 2u, and so on and so forth. So this is going to be phi 3. Write it here. Phi 2 equals to 2u equals to 3u. And so this is how these velocity potentials are going to look like here, right? So the velocity for this uniform flow, the velocity potentials are like this. They are linearly increasing. And then the velocity vector is going to be u everywhere, right? So it's u everywhere if you want to plot it. Okay, so this was a simple example, and now in the next session, I'm going to solve another example for a source flow. Okay, so this was for a uniform flow, and then in the next example, we are going to find the velocity potentials for a source flow.